Okay, in this session we're looking at velocity time graphs, and then later on we'll look at acceleration time graphs. But essentially, velocity time graph. Here we go, time, velocity, and we want and velocity up here, so let's go 10, 20, 30, 40, and I'll do this per second, and this is seconds. And so we may have a velocity time graph that may look something like that, for example. So there's a number of different things here. So that bit there, that slopes there, so in that we've got changing velocity, and of course the velocity is changing over some time, and so of course changing velocity on time will give us acceleration. Then we've got these flat sections, and these flat sections velocity is not changing, so we have constant velocity as well. So then there's another part, of course. If we drop a line down there, then I could work out the area of that in there, and of course area of a triangle is a half base times height, and in this case we've got a half of the time by, oops, let's go back on that one, the time by the, and the height is some velocity, and of course the velocity is distance over time, so we've got velocity times time, then would be the distance, so the area gives us the displacement. Alright, so let's have a look at an example. Okay, so here's an example we've got. It says, consider the velocity time graph obtained in vector sample 4 to find the following things. So anyway, what happened was what example 4 was saying is of no consequence. It's the graph that we've got here is what we are interested in. So part A is the acceleration in the first 6 seconds. So in the first 6 seconds, it looks at that bit there. So the acceleration is our change in velocity over the time it took. The change in velocity, of course, is v2 minus v1 over the time it took. v2 is 10, take 5 over 6, 5/6 of a second. Or I should say meters per second squared. Okay, that's part A. Part B says acceleration in the last 4 seconds. So that's from here to here. So again, the acceleration is v2 minus v1 over time. The final velocity is 0. The initial velocity is 10 over 4. So that would be negative 10 on 4, or negative 5 on 2 meters per second squared for that one. Alright, it says now, part C, the total displacement. So displacement is the area underneath the graph. So our displacement is all of that in there. So what have we got? Alright, well, what have we got? Well, we've got a couple of things. So let's get rid of all that. We've got those shapes there. So for our part C, I'll start it here and go over to the next page. We've got, first of all, we've got 4 different areas there we're looking at. So the displacement, which is related to the area, 5 times 6, plus that triangle, which is a half, times the base, which is 6, times the height, which is 5, plus that rectangle, and that rectangle goes from 6 up to 14, which is 8, times 10, and then the triangle area number 4, which is a half times the base, which is 4, times the height, which is 10. Okay, looks like I might be able to just squeeze it in there. And so when we figure out all of that, we get 145, and it's in metres because the velocity is metres per second. Alright, total displacement, total distance, well in this case it's all above the axis, so it's all positive area below the time axis. So if we had something that was down here, so it went down there like that, for example, and so we've got an area under here, like I've just indicated, then that comes out as a negative, and that negative indicates that it started to come back in the negative direction. So it's just something you need to watch for. Alright, not an issue in this case. Alright, next, acceleration time. Okay, acceleration time graphs tells us what the acceleration is at any time, and probably the best way to look at it is to look at an example. Alright, so here's our example. It says consider the motion of an elevator with velocity time graph as shown. Take positive values to represent upward motion. Alright, so we've got a velocity time graph, so it looks like we've got here, then it stopped, increases its velocity, gets to a certain one, stays that, and then it slows down and stops. I guess that's going up a floor. That's going up a floor, and then it stops to let people out, and then it comes back down, speeds up, goes constant, and then slows down and stops again. Alright, so let's have a look. It says in what sections OA, AB, BC, etc. is the lift accelerating positively? Okay, so the positive acceleration ones is where the gradient is positive, so there, and there. Accelerating negatively, oh, that's not right. What am I talking about? Positive gradient there and there. Negative gradient is there and there. So the ones I've circled in red are the positive gradient ones. They're the ones accelerating positively. And the blue ones are the one's a negative constant velocity, well they're the flat sections there and there. Okay, so we need to then determine the acceleration of each of the sections. So let's have a look. OA, the acceleration is the change in velocity 8/5. AB, acceleration 0. BC, change in velocity, it's negative this time, and it goes in 2 seconds. So -4. What have we got? CD, it stops there, so acceleration 0. DE, acceleration in that section, that 0 goes to -12, so it's a change of -12 over 2 seconds, which is -6. E to F, the acceleration there is 0, so it's flat. And then F to G, the acceleration there, its change in velocity increases from -12 to 0, so it's 12, 35 to 40 is 5. Alright, so there are the acceleration. So then we've got to sketch an acceleration time graph. So our acceleration time graph there's some negatives as well. We've got to go up to 40, 10, 5, 30, 35, 40. The greatest acceleration, -4 by the looks of it. So 1, 2, 3, 4. Okay. So OA, so the first 5 seconds it's 8/5. So in the first 5 seconds 8/5, it's 1 and a bit. So it's 8/5. The next bit, A to A, so that's 5 to 18 seconds, that's 0. 0. Then the next section, it's -4. And that next section goes up to 25. -4. The next section, 0 again, yeah. And that goes up to, where are we? What I've done there? Done something wrong here. Whoops, wrong way. Yep, stopped. Yeah, -4, that's right. Then the next section, it's 0 again. And that next section goes up to 25. Hang on, this one I've done too long. Then goes to 20, sorry about that. Then the next section, it's 0. It's flicking backwards and forwards. The next one's -6. So I didn't quite go far enough down there, so -6 is down here. We've got a bit at 0 again. And then the last, whoops, wrong way. The last bit, 12/5, so what's that, 2 and a bit. So there's our velocity, our acceleration time graph. Looks a bit messy, but anyway, you get the idea. Alright, start at ground level, 0 metres, determine its position at C and G. Alright, so what are we looking at? We're looking at for these we're looking at the 2 areas. Alright, So those two areas, there's a few different ways. They're trapeziums. You can use the trapezium formulas if you like. So O to C, our area is a half of the sum of the two parallel sides, 13 and 20, times by the distance between them, which comes out to 132 metres. Alright, so that's that area in there. So at C, it's at 132 metres. Now we need to know this area in here. And that area, because it's below the axis there, it's going to come out as negative. So that is the area between, well, C or D and G. So D to G, our area, is a half the length of the parallel sides, which is 15 and 8, times by the distance between them, which is minus 12 in this case. So it comes out to be negative 138. Okay, so at C it's 132 metres above the ground, then it goes down. So at G, its position is 132 minus 138, which is negative 6 metres. Alright, next question. Average velocity. Alright, velocity is displacement over time. We've just found the displacement is minus 6 and 40 seconds, and if you do that in your calculator you get negative 0.15 metres per second. Alright, so that's part E. Part F is asking for the how far, that's the distance. So the distance we don't take into account. We don't take into account the negative here. Alright, that's displacement. That negative tells us the direction. Alright, so it tells us it's gone this much that way and then it's gone that much there. So we want the distance that whole lot. Alright, that bit from there to there, plus that bit from there to there. Just the length of it. Alright, so that would be, our distance is the 132 plus the 138, which is 270 metres. And then finally G asks us the average speed, so oops, let's change. Speed is distance over time, and the distance is 270, the time is 40, and so you get 6.75 metres per second when you do that calculation. Alright, so that's our next set, problem question set number 2, all ready to go.